This research presentation is about vibration suppression of a harmonically forced oscillator using a passive nonlinear vibration observer. My name is Bo Yu, and I am from the Department of Mechanical and Industrial Engineering at the University of Wisconsin-Platteville. In this presentation, first I will give you a brief introduction. The mathematical model of a nonlinear vibration observer will be given. The methodology which I'm going to use to calculate the analytical solution will be introduced. Some analytical results are calculated using the methodology will be presented. Numerical simulation are then compared with analytical solutions for different parameters. Then finally, I will wrap up these presentations. Vibration observers are widely used in engineering structures, such as electrical transmission cables, skyscrapers, and bridges. High-rise structures and cables will experience along-wind vibrations and crosswind vibrations or earthquake loads. Whereas bridges are subjected to traveling loads such as moving crowds. However, the random load scenario leads to a different approach to determination of optimal parameters and not considered in these studies. In this study, we are mainly going to focus on the deterministic harmonic loads. Two mass damper consisting of secondary mass, a viscous, and an elastic spring are commonly attached to the vibrating primary system for suppressing the undesirable vibrations. Closed-form optimal design series are only available for simple systems, for example, a 2 degree of freedom mass spring damper system. So usually they are linear system. A standard tune vibration observer is a single degree of freedom system which can be used to suppress a troublesome resonance or attenuate the vibration of a structure at a particular forcing frequency. Presuming that the main structure is also represented by a single degree of freedom system, there are three variables which can be selected by the vibration observer designer to tune the performance of the observer. The frequency ratio, the vibration observer damping ratio, and the mass of the observer. Generally, the mass ratio between the main system mass and the observer mass is usually assumed as a constant. For this reason, most of the published work only consider themselves with two design variables. Another approach is using nonlinear devices. For nonlinear vibration observers, the study is generally interesting because the phenomena that may occur that do not happen in their linear counterparts. One of the earliest studies on nonlinear vibration observer was the work by Robertson. He investigated the performance of an undamped nonlinear vibration observer and concluded that the observer's effective bandwidth improved significantly when a nonlinear vibration observer is used instead of a linear one. Later on, there are extensive work were carried out on the nonlinear vibration observer. Another work was done by Swan and Jordan. They studied the optimal parameter design of a linear and nonlinear dynamic vibration observer for a damped primary system. They investigated the optimization criterion other than the traditional measures and obtained a small improvement in the steady-state response by using nonlinear springs. In this research, the analytical solution of a periodic motion in a nonlinear vibration observer will be obtained. The vibration effectiveness under different nonlinearity are considered. The nonlinear phenomenon was observed when the strength of the nonlinearity is increased. This is the mechanical model of a nonlinear vibration observer. M1, that's the main structure. M2, it is a nonlinear vibration observer. The governing equation of nonlinear vibration observer can be written as equation 1. The structure can be modeled as a linear spring and a damper with coefficient K1 and C1. C2 times x2 prime minus x1 prime, K21 multiply x2 minus x1, and plus K22 multiply x2 minus x1 cube. are the linear damping force and the nonlinear spring force from the nonlinear observer respectively. Omega is the driving frequency, the operator prime that represents the derivative with respect to time. With the introduction of the following parameters in equation 3, the non-dimensional governing equation can be expressed as equation 2, where Z1 and Z2 are the damping factor, mu is the mass ratio, beta is the tuning factor, alpha is the strength of nonlinearity, p is the static displacement, tau is the non-dimensionalized time, omega is a non-dimensional frequency. The dot represents the derivative with respect to the non-dimensional time. The method of generalized harmonic balance can be used to solve the equation of motion that were previously derived. The standard form of equation 1 can be written as x double dot plus fx x dot tau equals 0, where the x equals x1 and x2 transpose, x dot equals x1 dot x2 dot transpose, and f equals f1 f2 transpose. The analytical solution of the periodic motion for the above equation can be represented by using the finite Fourier series, where x1 it is the displacement of m1, x2 it is the displacement of x2. A naught tau equals a2 naught tau minus a1 naught tau, bk tau which equals b2k tau minus b1k tau. ck tau equals c2k tau minus c1k tau. Then we can take the first and second order derivative of x1 star tau and x2 star tau to obtain the velocity and the acceleration. Now let's define vector a naught, which include a1 naught, a2 naught, vector b equals b11, b12 until b1n, b21, b22 until b2n. And vector c equals c11, c12 until c1n, c21, c22 until c2n. Then we can substitute equation 6 to 8. So that is x1, x2, x1 dot, x2 dot, x1 double dot, x2 double dot, back into equation 2, which that's the equation of motions. And average for the harmonic terms, cosine k omega tau and sine k omega tau. And we can obtain equation 10, where the analytical expression for f1, 0, f1 kc, f1 ks, f2, 0, f2 kc, f2 ks are given in equation 11. Then we can define vector z equals a0 bc, z1, that is the time derivative of z. The first 4n plus 2 equation can be written into a form of vector field as z dot equals z1 and z1 dot equals gzz1, where gzz1 is given in equation 14, k1, k2, f1, c, f1s, f2c, f2cs are given in equation 15. To find the steady state periodic solutions, we need to let y dot equal 0. Then equation 14 can be rewritten as equation 17. The 4n plus 2 equations in equation 17 can be solved by using the Newton-Raphson method. Once we obtain the solution, we can linearize the equation y dot equals fy at the equilibrium point, y star equals z star 0, delta y dot equals df y star multiplied delta y, where the df y star equals partial f partial y at the equilibrium point y star. The corresponding eigenvalue of the df matrix can be used to determine the stability of the system. The eigenvalues of the df are classified as n1, n2, n3, n4, n5, n6, where n1, n2, n3 are the number of negative, positive, and zero real eigenvalues respectively, and n4, n5, n6 are the total pair of number of complex eigenvalues with negative, positive, zero real part respectively. Now let's look at some analytical predictions. First, we can rewrite the solution in terms of the amplitude and the phase, where the harmonic amplitude aik equals root square b1k square plus c1k square, and the phase phi ik equals arctangent cik over bik, where the I equals 1, 2, which 1 stands for mass 1, 2 stands for mass 2. Consider the system parameter as z1 equals 0.08, z2 equals 0.1, mu equals 0.1, beta equals 0.909, and p equals 0.05, and we can find the analytical results. In this slide, The first harmonic amplitude of both M1 and M2 are investigated for different nonlinearity alpha. Figure A presents the first harmonic amplitudes of both M1 and M2 with a weak nonlinear strength, alpha equals 0.5. The red solid curve represents the first harmonic amplitude of M2. The black solid curve represents the first harmonic amplitude of the main structure M1. The effectiveness of the nonlinear vibration observer can be observed as both resonance peaks of the primary oscillators are suppressed. To examine the outcome of nonlinear vibration observer with respect to the nonlinear stiffness, the nonlinear term of the stiffness was varied from 0.1 to 1.0 without changing the other parameters. Figure B to figure D presents the first harmonic amplitude A11 and A21 of different alpha. The first peak amplitude of M1 at the lower frequency increases as the nonlinear strength alpha increases. However, the second peak amplitude of M1 decreases as the alpha increases, with the amplitude of M2 remaining almost the same. The first peak frequency of M1 shifts to the higher frequency, and the second peak frequency of M1 shifts to the lower frequency as alpha increases. When the nonlinear term is kept increasing, in figure A, the nonlinear term alpha equals 10, the unstable solution can be obtained. The jumping phenomenon occurred at the settlement bifurcation. The hopeful bifurcation are at omega equals 1.15 and 1.23, where the solution changed from stable to unstable. The magnitude of the first peak of M2 decreased to 1.0 from 1.5 as alpha increased from 1.0 to 10.0. And the second resonance peak seems flattened out due to the strong nonlinearity alpha equals 10. The magnitude of the first resonance peak of M1 increases. The effectiveness of the vibration reduction is undesirable. In figure B, the nonlinear term alpha equals 30. Compared with figure A, another branch of unstable solution appears around the first peak. Now let's look at some numerical results. In this slide, the phase trajectories and the displacement time history plot are presented for the nonlinear vibration observer at the first resonance when the value of the nonlinear term alpha equals 0.1. The initial conditions for numerical simulation are computed from the approximated analytical solution with 10 harmonic terms. Black and the red solid curve are used to represent the numerical results of M1 and M2 respectively. Black and the red circular symbols are analytical solution of M1 and M2 respectively. The initial conditions are represented by the large red and black solid circles. The trajectory of the first resonance peak are presented in figure A for omega equals 0.83, with initial conditions are computed by the analytical solutions. It can be seen that the numerical solution matches the analytical solution well. Figure B presents the displacement time history plot for M1 and M2. The periodic motions of M1 and M2 at the first resonance peak are in phase, which resemble the first mode of the linear vibrations. The amplitude spectrum AIK, I equals 1 and 2 of the M1 and M2 are presented in figure C and D. The values of the harmonic amplitudes when K is even number are all zeros. The next harmonic term, A19 and A29, are almost approach zeros. In this presentation, the performance of a nonlinear vibration observer is investigated through the generalized harmonic balance method. The harmonic amplitudes of the primary mass and also the observer are presented. Based on the analytical results, the vibration mitigation is more effective around the second peak with the increase of the spring nonlinearities. However, the vibration observer becomes less effective around the first resonance peak. Unstable motions and bifurcations are observed as the nonlinearity strength is increased. Finally, the numerical simulation around the first resonance peak is presented. Thank you.